Welcome to third sem Diploma Electrical LMSE content. Subject DC machines and alternator. Unit 2 Performance of DC generator. Session 13 Characteristics of DC generator. Students, why we need to study the characteristics of DC generator? Characteristic study is behavioral study of the DC generator. That is, here we study how DC generator behaves on no load, how DC generator behaves on load. That will help you to select a particular DC machine for a particular application. In this session, you will study types of characteristics, characteristics of separately excited DC generator, characteristics of self-excited DC generator, critical field resistance, critical speed, voltage buildup. Types of characteristics. Following are the three most important characteristic or characteristic curves of a DC generator we commonly study. They are number 1, no load characteristic or OCC. It is a curve drawn between no load induced EMF E0 versus field current IF at constant speed. Second one, internal or total characteristic curve. It is the curve drawn between actual induced EMF E versus armature current IA. This characteristic is mainly interested by the designer. The third one is external or load characteristic, which is the curve drawn between load terminal voltage V versus load current I or IL. Now let us see the characteristics of separately excited DC generator. In that, the first one, no load characteristic. As already mentioned, it is the characteristic curve drawn between no load induced EMF versus field current IF at constant speed. Here in figure, A represents the circuit diagram and B is the characteristic curve. The necessary excitation current is taken from external independent DC source, and the excitation current is varied with the help of potentiometer, and excitation current is measured by an ammeter connected in the field circuit. The voltmeter is connected across the armature of the DC mode generator to measure the induced EMF. You know that the voltage equation of DC generator is given by E is equal to 5Zn by 60 into P by A volts. As the speed is constant, then the generated EMF equation will become E is equal to K phi. That indicates if the excitation current is varied from small value, the phi and hence induced EMF increases up to the saturation. That is, as field current increases, flux produced by the field pole increases, induced EMF increases. That is shown with a straight line OD in the characteristic curve. As the field current is increased, the flux produced by the pole increases and flux density increases. Due to that, field poles are saturated. After that, any increase in the field current will increase the induced EMF slowly. That is represented by a bent curve dB of the curve ODB. This is how the no load characteristic can be obtained for separately excited DC generator. Now we'll see internal or total characteristics curve, which is the curve drawn between actual induced EMF E versus IA. Consider if E0 is the rated no-load induced EMF produced by a generator at some fixed field current. At no load, the armature reaction drop and armature resistance drop are negligible. Hence, E0 is almost constant. That is represented by curve 1. But when generator is loaded, the armature reaction drop increases as load current increases. Then, if you subtract from E0 the voltage drop due to armature reaction for different loads, we get E, that is actual induced EMF in the armature at different load. Then we can plot curve 2 for different loads in this way, and that is called as internal characteristic curve for the generator. Now we will discuss external or load characteristic of separately excited DC generator. This characteristic curve, it is the curve drawn between load terminal voltage V versus load current I or IL. This can be obtained from internal characteristic. So the straight line OA is the IA-RA drop for different armature current. If we subtract the ordinates of IA-RA drop from curve 2, we obtain the curve 3, which is the value of V for different armature current. The V is the load terminal voltage across the load terminals that we can obtain, that is V equal to E minus IA-RA. The curve 3 is called as load characteristic curve, that indicates as load increases, the induced EMF of the generator decreases. The curve is dropping. Okay, now we will see the characteristics of self-excited DC generator. First, we see the no-load characteristic or OCC, which is the curve drawn between no-load induced EMF E0 versus field current IL. OCC for self-excited DC generator, whether it is a shunt generator or series generator, are obtained in similar way. That is, by disconnecting the field winding from the machine and connecting it to the DC source, the field current can be varied with the help of rheostat connected, and it is measured by an ammeter connected in the field circuit. The machine is driven at constant speed with the help of prime mover, and generated EMF is measured by a voltmeter connected across the armature. Okay. Then by varying the field current with the help of rheostat, note down the readings of an ammeter and corresponding induced EMF by the voltmeter. get the curve as shown in the figure, which is the no load characteristic curve. DC shunt generator in the field winding, there exists some residual flux. Due to that residual flux, a small amount of EMF is induced even when field current IF is 0. That is represented by OA. That is why the curve starts from little above. Initially, the curve is a straight line, that is at lower flux densities, that is before the saturation is reached. As field current increases, the flux increases and hence induced EMF increases. After point B, once saturation is reached, a large amount of field current is required to increase a small amount of induced EMF. That is why the curve bends here. So this is how we can obtain the OCC or self-excited generator at some constant speed. You should note that OCC for the higher speed lies above this curve and OCC for the lower speed lies below this curve. Now let us see critical field resistance for shunt generator. What is critical field resistance? The maximum value of shunt field resistance above which the generator just fails to build up its voltage. That is, generator will fail to generate its voltage is called as critical field resistance. Let us see the critical field resistance in detail. The generator, shunt generator is started and is operated as a shunt generator. You know that already in the field winding there exists some residual flux. Due to that, some EMF is induced in the generator that circulates some current in the field winding. And that current again strengthens the field flux, that will increase the induced EMF, and hence field current is increased. This reinforcement of induced EMF and field current will continue till some equilibrium is reached at some point T on the OCC. And then draw a field, a line from O, that is a resistance line of the shunt field winding that cuts at P, at that speed. So then OL represents the maximum EMF generated by the shunt generator at R as the field current. If the field winding resistance is decreased less than R, then that will cut the OCC at B. Then corresponding point M on voltage axis, the generator, that is OM, is the maximum EMF induced by that generator with reduced shunt field resistance. Suppose if we increase the shunt field resistance above the value R, then the maximum value of the induced EMF by that generator decreases. If we keep on increase the resistance like that, if the resistance line does not cut the OCC, so then generator will fail to build up its voltage. So that means, so here the resistance line RC, it just touches the OCC. That is, this is the maximum shunt field resistance at which generator will just excite. That is, it will just generate the voltage. Any increase in the resistance above this value, the generator will fail to build up its voltage. So, and critical field resistance at a different field, different speed will be different. Okay. Then how to find the critical field resistance RC of a shunt generator? For that, first you have to plot the OCC from the given data. Then draw the tangent to its initial portion of the curve. That is a straight line. The slope of this curve gives the critical resistance for the speed at which the data was obtained. Then how to draw OCC at different speeds? We know that OCC for a different speed is different curve. So suppose we have OCC for the fixed speed n1. At a constant speed n1, we have open circuit characteristic curve like this. Then we can get OCC for any other speed, say for example n2, from the OCC for n1. For that, we know that from the voltage equation, E is proportional to N for any fixed excitation. Then we can deduce the relationship for both the speeds N2 and N1. That is, E2 by E1 is equal to N2 by N1, or from this we can get the value of E2 is equal to E1 into N2 by N1. From this curve, that is OCC for N1, for field current IF, the value is OH. We have the value of E1 is HC. From this, we can get the new value of induced voltage E2 at speed N2. From this equation, E2 is equal to E1, the value of E1 from the OCC for N1 is HC into N2 by N1. N2 is the new speed, N1 is the existing characteristic OCC at N1. So that we will get the point HB. That is, point D is located in this way. It is the one of the point of the OCC at another speed N2. In this way, other points can be found and we can draw the new OCC at another fixed speed N2 from the OCC for N1. Now we will see what is the meaning of critical speed NC. Critical speed of the shunt generator is that speed for which the given shunt field resistance represents critical resistance. That is, it is a speed at which RSH itself represents the critical resistance. In the given figure, curve 2 corresponds to critical speed because here RSH line is tangent to the OCC. So Any speed below this generator will fail to build up its rating. This is the meaning of critical speed. Now we will see voltage build up of a shunt generator. Before loading any shunt generator, it is first allowed to build up its rated voltage. That is, any shunt generator, if we start, there exists some residual magnetism, and due to that residual magnetism, some EMF is induced in the generator. That induced EMF will circulate some current in the field winding, and that current will increase the flux if the field winding is connected properly with regard to polarity. That increased flux again increases the induced EMF and hence induced current, and that again strengthens the field flux. This process will continue till still the saturation is reached at some point. So that is explained again with the help of this OCC. Here in this diagram, OA represents EMF induced due to residual magnetism. That will circulate the field current OB in the field winding. This current along with the residual induced EMF, initial current, it will induces further more EMF OC. So that increased EMF again circulates more current OD in the field winding, and this more current again increases the more induced EMF, and it will go on till the equilibrium is reached. That is how the voltage build-up takes place. That is, voltage build-up means a generator generating its rated voltage at rated speed. Any shunt generator, before loading, it has to be first build up its voltage. Then only load can be applied on the generator. To build up this voltage, certain conditions has to be satisfied. Otherwise, generator will fail to build up its voltage. They are called as conditions for voltage build up of a DC shunt generator. If generator fails to meet these conditions, it will fail to build up the voltage. That means generator will not generate the voltage. Those important conditions are: there must be some residual magnetism in the generator poles. If field pole does not have any residual magnetism, generator will fail to build up. To build up the voltage, there must be some residual magnetism present in the field poles. Second one, for the given direction of rotation, the shunt field coil should be correctly connected to the armature. This is very important. With regard to polarity, the shunt field coils must be properly connected. Like previously we have studied, initially due to the residual flux, some EMF induces. That induced EMF circulates current in the field winding that produces the flux. Both flux must add to strengthen the induced EMF. That both these two flux must be added. For that reason, the field coils must be connected properly. If these two fluxes get cancelled, then they do not build up its voltage. That is the reason the field flux produced must aid each other to build up the voltage. The third important point is if generator is excited on open circuit, then its shunt field resistance must be less than critical field resistance that we have studied already. If it is excited on load, the shunt field resistance RSH must be more than certain minimum resistance, which actually is determined by the internal characteristic of the DC generator. The speed of the generator should be higher than critical speed to build up the voltage. Then these conditions must be met. There are some factors which will affect the voltage building up of the DC generator. Those are reversed shunt field connection, reversed rotation, reversed residual magnetism. To understand these adverse effects to the voltage building up, let us see with the help of these four diagrams. In figure A, a normal operation is shown in which generator is rotating clockwise. Both field flux and residual flux. Phi F is the field flux due to field current. Phi R is the residual flux. Both are shown towards the left. That means they aid each other. Now we'll see these adverse effects one by one. Suppose if the shunt field connection is reversed. Reversed shunt field connection will produce the flux in reverse direction. That as we have shown previously. Phi F reverses, that is Phi F, the field flux opposes the residual flux here. To build up the voltage, both the flux must add together. So here, due to the reversed shunt field connection, due to the reversed field flux as that of the residual flux, the field flux Phi F opposes the residual flux Phi R. Here, generator, instead of building up, generator builds down from the initial residual induced EMF. In the next case, that is, if the rotation is reversed. If the generator rotation is reversed, again it builds down from the initial induced EMF due to the residual flux. That is, induced EMF reverses and reversed, that circulates the reversed field current. Again, that will produce the reversed flux in the field winding. That is, in this case also, again, Phi F, which is opposite to the Phi R. Field flux opposes the residual flux, and again generator builds down from its initial residual value. The third case, that is, if the residual magnetism is reversed, that is, if Phi R reverses. If Phi R is reversed, the reverse generator produces EMF in reversed direction and circulates the current in reversed direction. That reverses the field flux. So here both residual flux and field flux are in the same direction, that is in the opposite direction of the normal operation. But they aid each other, but they are in reverse direction. In this case, generator will build up the voltage in reverse direction. Thus, in the normal operation, it generates the voltage. Its polarity is shown here, plus minus. Here it is minus plus. If residual magnetism is reversed, if residual flux is reversed, generator will builds up its voltage in reverse direction. Even it is possible to change the residual flux. For that, there is a process. You have to remove the field winding from the armature, field winding from the machine, and connect it to the external DC source with proper polarity as is required. Then you increase the field current, and then it will retain the residual flux with the required polarities. The process is called as field flashing. So these are the factors which affect the generator's voltage building up. Okay, now we will see the external or load characteristic of self-excited DC generator. It is the characteristic curve drawn between low terminal voltage V versus load current I or IL. You know that the shunt generator, as load on the generator increases, its voltage drops due to the effect of armature reaction and effect of armature resistance drop, and due to these two drops the voltage drops, and due to that decreased voltage even field current also decreases. Due to that again the reduction in voltage takes place. The external characteristic curve can be drawn. Figure A indicates the circuit diagram. This diagram is characteristic curve. As shown in figure, A1 measures, ammeter A1 measures the field current, A2 measures the load current, B measures the load terminal voltage. With the help of field rheostat, the field current can be varied. Before loading the generator, first, as we discussed already, generator has to be built up its rated no load terminal voltage first. After building up the voltage by keeping the field current IF constant with the help of this rheostat, gradually increase the load and note down the reading of load current and corresponding load terminal voltage. And if we plot the curve for various load currents, we obtain the curve as shown in the figure. In the characteristic curve, the OA is the EMF induced at no load. As load is increased, due to the armature reaction and armature resistance drop, voltage starts decreasing. This is called as dropping characteristic. Initially, as load is increased, load current increases, voltage drops up to the point B, which is called as breakdown point. This portion AB is called as working portion. Generator can be loaded in this region. Beyond point B, any attempt is made to increase the load. Increasing the load means by decreasing the load resistance. As load increases, load current has to increase. Instead of increase in the current, current suddenly starts decreases. This is because of severe voltage drop due to the armature reaction and armature resistance drop. The decrease in terminal voltage decreases the load current. If you keep on increase the load at some point of time, the armature will get short circuit. So that is why generator cannot be loaded beyond this point. This is the safe operating point. Next, the internal or total characteristic of self-excited DC generator. It is the characteristic curve drawn between E versus IA. As it is mentioned already, it can be obtained from external characteristic curve. To draw this internal characteristic curve from external characteristic, you just follow these points to obtain the internal characteristic curve. First, draw the external characteristic line AB shown in the figure. Then draw the field resistance line OB as usual. That is as usual in the sense with the obtained data for the field winding. The horizontal distance from OY line to the line OB, this distance, use the values of field currents for different terminal voltages. If we add these distance horizontally to the external characteristic line AB, then we get the curve for the total armature current. That is this dotted curve AC. Then draw armature drop line OR, right? The armature drop line, that is IARA line OR, again as usual. If brush contact resistance is assumed constant, then armature voltage drop is proportional to the armature current. As armature current increases, IARA drop increases. For any armature current in this curve OK, the armature voltage drop IARA is equal to MA. If we add these drops ordinates of the curve, if we add these ordinates of the curve to curve AC, we get the internal characteristic for example ST. We get the point T. That is ST equal to MK. The point T lies on the internal characteristic curve. Like that, we get one point. Similarly, we can form different points for different armature currents to draw the complete internal characteristic curve. So far we have studied various characteristics of separately excited and self-excited DC generator. Based on that, now we will do some exercises, simple exercises with the help of multiple choice questions to test what we understood from the session. The first one, a shunt generator do not build up any voltage at no load because the choices are shunt coil may be connected in reverse direction, there is no resistance, magnetism in the poles, its a shunt field resistance is more than physical resistance, any one of the above. Answer is D. You can think over it. Right? The question is, a shunt generator do not build up any voltage at no load because Nth coil may be connected in reverse direction. There is no resistance, residual magnetism in the poles. A shunt field resistance is more than critical resistance. These all are the factors which are affecting the voltage field that we have studied already. That is why the answer is any one of the above. Second one. Critical resistance is the resistance of the field winding of a generator. Four options at which it develops maximum voltage, at which it supplies maximum power, beyond which it cannot develop any voltage. D. At which the speed of generator is infinity. Answer is C. That is beyond which it cannot develop any voltage. That is one of the conditions for voltage buildup of the generator. We have studied already. Critical resistance is the resistance of the field winding of generator beyond which it fails to excite, it fails to build up its voltage. Third one, the load characteristic of a generator is the curve between V versus I. We have studied already, right? Among the choices A, B, C, D, where is that load current is I, terminal voltage is V. So that is why C is the answer. Fourth one. The internal characteristic of generator is the curve between, we discussed already, that is E versus I, IA. That is, IA is armature current and generated EMF. The answer is A. Fifth one. Main reason for breakpoint in the load characteristic of a DC generator is armature drop, armature reaction, both A and B, none of these. Main reason for breakpoint in the load characteristic of a DC generator is armature reaction. Okay. Sixth one. Which of the following type of DC generator gives constant output voltage at all loads? Which of the following type of DC generator gives constant output voltage at all loads? It's a compound generator. And generator having dropping characteristics, right? Series generator, as load increases, field flux activity you have studied already, right? So the level compound generator gives constant output voltage at all loads. The critical resistance of DC generator is the resistance of field winding. But it is not the resistance of armature, it is not the resistance of load, not the resistance of pressures. It is the resistance of field winding. Answer is P. Eighth one. If a DC generator fails to build up, the probable cause could not be. We are just sometimes questions will be asked like this. We have studied the factors affecting the voltage build-up, factors which makes generator fail, factors which affects the voltage build-up. But here, if a DC generator fails to build up, the probable cause could not be imperfect brush contact, field resistance less than the critical resistance, no residual magnetism in the generator, faulty shunt connection, we can need to reduce the residual magnetism. The answer is P. Right? The probable cause should not be field resistance should not be less than critical resistance. Field resistance less than critical resistance. Next, in a DC generator, magnetization characteristic equal to external characteristic. External characteristic, magnetization characteristic minus unit drop minus armature reaction. External resistance equal to internal characteristic minus armature reaction. Internal characteristic equal to magnetization characteristic minus unit drop. Right? You have studied previously. The answer is B because external characteristic we can obtain from the magnetization characteristic, that is from OCC. Subtracting E0 minus armature reaction drop, we get E. Subtracting from E, voltage drop due to ohmic drop, we get V. That is external characteristic. Okay. Now try to do these activities based on what you studied in this session. Right? It's already covered in this session. Let's try to do these activities. Draw the external characteristic of separately excited DC generator. Draw the internal characteristics of separately excited DC generator. Draw the OCC of a DC shunt generator and determine the critical field resistance. List the applications of series generator. Try to list the application of shunt generator. Thank you.